In this video, I'm going to talk about the concept of vector and the operations that you can perform with vectors. Here is the list of topics that will be covered in this video. First, we will briefly talk about the scalar and vector quantities. We will then discuss the vectors in a two-dimensional space. After that, we will introduce our notation for working with vectors. Then we will discuss the concepts of length of vectors, addition of vectors, scalar multiplication, subtraction, and unit vector. We will then extend the concepts to three-dimensional space and finally to a general n-dimensional space. So let's get started. In general, we can have different types of quantities such as scalars, vectors, and tensors. Let's focus on scalar and vector quantities here. So what is a scalar? A scalar is a quantity that can be fully defined with just one piece of information. In other words, a scalar quantity has only one attribute, and that is the magnitude. For example, length, mass, and temperature can be represented by numbers such as 80 meters, 10.5 kilograms, and -5 degrees C. But now imagine that your friend is asking you about the address of a location and you respond, go 2 miles. Obviously that is not enough, and your friend would most likely ask, in which direction? That is exactly the concept of vector. A vector is a quantity that is fully defined with two attributes, magnitude and direction. So getting back to our imaginary scenario, if you tell your friend, for example, go 2 miles to the north, then they should have enough information to find the location. As a recap, vector is a quantity with two attributes, magnitude and direction. Now let's consider a two-dimensional space. In this coordinate plane, we have shown points A and B, and the vector going from A to B. Let's see how we can introduce this vector. Since the vector goes from A to B, we call this vector quantity AB and put an arrow symbol on top to show that AB is a vector quantity. So this was the name of the vector quantity. But what about its value? By looking at the coordinate plane, we can see that the vector AB goes 1 unit in the negative x direction and 3 units in the positive y direction. We call each of these values a component of the vector AB. For example, here, the x component is -1 and the y component is 3. There are various ways to show a vector's value. The idea is to somehow enclose all the ordered set of components of the vector. One way is to enclose these components between parentheses. We can also enclose them between angle brackets, or we can even show them as a row vector or a column vector. These are all common notations that you may see people use when working with vectors. The important thing is, though, that the order of components needs to be preserved. Conventionally, the x component comes first and the y component comes after that. Now let's look at another example. We have a vector going from C to D. So we call this quantity CD and put an arrow symbol on top to emphasize that CD is a vector. Regarding the value of this vector, we can see that it goes 2 units in the negative x direction and 4 units in the negative y direction. So the x component is -2 and the y component is -4. And we can show this quantity in any of the previously mentioned fashions. Before talking about the operations you can perform with vectors, I'd like to emphasize an important point here. Remember we said a vector has two attributes, magnitude and direction. We did not say anything about the initial and or ending points of a vector. That means initial and ending points are not attributes of a vector. In other words, vectors are free. You can grab a vector and freely move in the coordinate plane. And as long as its attributes, which are the magnitude and direction, are preserved, the vector's value will remain the same. For example, in the coordinate plane shown here, all the vectors we have shown have the same value. So all the vectors OP, QR, and ST are equal, and their components are -1 and 3. Now that we have become familiar with the concept of vector and the common notations, let's talk about the length of a vector. The length of a vector like A can be shown this way. Now, how can we calculate the length of vectors A, B, and C, D that are shown here? It turns out that we can resort to the Pythagorean theorem. So for a right triangle like this, we have c squared equals a squared plus b squared. Now if we look at the vector AB, we can see that this vector and its projections on the x and y axis can form a right triangle. Two short sides of this right triangle are 1 and 3 units long, so the hypotenuse will be the square root of 1 squared plus 3 squared, which will be the square root of 1 plus 9, and finally we get the square root of 10. And the length of the vector AB is then equal to the square root of 10. Similarly, in the case of the vector CD, we can consider a right triangle with the short sides of 2 and 4 units long. The hypotenuse is then equal to the square root of 2 squared plus 4 squared, which equals the square root of 4 plus 16, which becomes the square root of 20. So the length of the vector CD then equals the square root of 20. Now let's see how we can add two vectors. For example, for the vectors AB and CD shown here, what is the addition of AB and CD? So remember we said vectors are free. That can be very useful. We can move the vector AB, which is named A here for simplicity, and bring its initial point to the origin of the coordinate system. We can then move the vector CD, which is named B here, and place it in such a way that its initial point is at the ending point of the vector A. So now imagine you are giving your friend the address of a location in two consecutive steps. In the first step, you give them the address of a location represented by a vector like A, which is -1 unit in x and 3 units in y direction. And once they get there, they need to follow a new address represented by the vector B, which is -2 units in x and -4 units in y direction. If you could give the address of the final location in one single step, that would be -3 units in x and -1 unit in y direction. In other words, the addition of vectors A and B is equivalent with a vector with the components of -3 and -1. So in order to find the addition of two vectors, we can first write them in the vector notation. We then add the first components to each other. Similarly, we then add the second components, and we can see that the results are the same as what we obtained previously using the coordinate plane and drawing the vectors, except that now we know how to easily find the addition of vectors without drawing the vectors on a coordinate plane. So as a recap, to add two vectors, you just need to add their components to each other. Now let's see how we can multiply a vector by a scalar. For example, for the vector a shown here, how can we calculate the vectors 3a and minus 2a? So for multiplying a vector by a scalar, the direction will remain the same if the scalar is positive, but the direction will be reversed if the scalar is negative. The length of vector will also be scaled by the absolute value of the given scalar. For example, 3a means a vector in the same direction as a, but with a length of 3 times as large as that of a. And if you draw such a vector on the coordinate plane, you will see it will be the vector of minus 3 and 6. Similarly, minus 2a is a vector in the opposite direction of a with a length of 2 times as large as a. So by drawing that, we can see that it will be the vector of 2 and minus 4. So in order to multiply a vector by a scalar, we can multiply the components of the vector by the given scalar. For example, to find 3a, we can simply multiply all the components of a by 3. And we can see that the results are going to be the same as what we obtained before using the coordinate plane. Similarly, to find minus 2a, we can simply multiply all the components of a by minus 2, and we can see that the result is going to be the same as what we obtained before by drawing the vectors on the coordinate plane. Now let's see how we can subtract one vector from another one. Let's say we have two vectors, a equals ab and b equals cd. How can we calculate ab minus cd? In order to find a minus b, we can rewrite it as a plus minus b. We can then find the addition of vectors a and minus b as before. In order to do that, we draw both vectors a and minus b on the coordinate plane. Since the vectors are free, we put the initial point of a on the origin and the initial point of the vector minus b on the ending point of the vector a. We can then see that the addition of a and minus b will be the vector of 1 and 7. Now let's see how we can calculate a minus b without drawing anything. We have the vector a with known components and the vector b with known components. We can write them in the vector notation, and then we subtract the x component of b from the x component of a. Similarly, we can subtract the y component of b from the y component of a, and we can see that the results are going to be the same as what we obtained before. So in general, for subtracting a vector like b from another vector like a, you just need to subtract the components of b from those of a. Now let's talk about a new concept, unit vector. Unit vector is just a vector with the length of 1. So for any given vector like a, we can find the corresponding unit vector in such a way that the direction of the unit vector is the same as the direction of the vector a, but the length of the unit vector is just 1. In order to do that, we just need to multiply the vector by the reciprocal of its length. Now This new vector has the same direction as A since it's just the multiplication of the vector A with a positive scalar. On the other side, we can show that its length also equals 1. To do that, we can write the expression that we have for the length of a vector. Now, since the length of the vector A is a positive scalar, it can be taken out, and at the end, the length of the vector A will be cancelled out from top and bottom, and we end up with just 1. So the length of this vector is indeed 1. Now, let's take a look at a simple example. We have a vector A with the x and y components of -1 and 3 respectively. We want to find its corresponding unit vector. The first step is to find the length of the vector. The length of this vector equals the square root of -1 squared plus 3 squared, which is the square root of 10. Now we multiply the vector A by the reciprocal of this length, so we just need to multiply all the components of the vector A by the constant 1 over square root of 10, and we will obtain the unit vector's components to be -1 over square root of 10 and 3 over square root of 10. Now let's extend the concept of vector to three-dimensional space. Everything is pretty much the same as before, except that now the vector has 3 components in x, y, and z directions. For example, a vector like A that goes ax units in x direction, ay units in y direction, and az units in z direction can be shown as an ordered set of components using one of the previously mentioned notations. And we can also extend all the operations we discussed to a three-dimensional space. For example, if we have 2 vectors like A and B, for addition of these vectors, we just need to add the corresponding components. For subtraction, we need to subtract the corresponding components. And for multiplication by a scalar, we just need to multiply all the components by the given scalar. We can also find the length of a vector as the square root of the summation of every component to power 2. And from the definition of the unit vector, we can then find the unit vector for a given vector like A. Now, let's take a look at an example. Let's say we have 2 vectors A and B, as shown here. To find A plus B, we can simply add the corresponding components, which results in a vector like this. To find A minus B, we can then simply subtract the corresponding components, and we're going to get this result. If we want to find 2A, we just need to multiply the components of A by 2, and we will then obtain this vector. In order to find the corresponding unit vector for A, we just need to first find the length of the vector A, which is going to be the square root of 0 squared plus minus 3 squared plus 4 squared, which turns out to be just 5. And finally, we can use the definition of the unit vector, and the result will be like this. Finally, we can extend the concept of vector to a general n-dimensional space. For example, we have if we have 2 vectors like A and B, then for addition of these vectors, we just need to add the corresponding components. For subtraction, we just need to subtract the corresponding components. For multiplication by a scalar, we just need to multiply all the components by the given scalar. And finally, we can find the length of a vector as the square root of the summation of every component raised to power 2, and from the definition of the unit vector we can find the unit vector for a given vector.